Ecco, infatti io vedo recording.
Sì.
Ok.
No, direi che possiamo far partire la cabina.
Sì.
Ok, adesso facciamo partire. Serena, ci sentite adesso? No, no, io questo ce l'ho. Allora tu
aspetta,
hai...
io però... Guarda un
Stacchi
po'.
tu, sei a posto.
Stacco.
Vediamo. Però...
Allora, Serena dice che sente ma con riverbero. E adesso come sentite? Faccio così.
Sì, praticamente credo che ci siano due microfoni accesi che vanno in conflitto, probabilmente.
Sì, stiamo cercando di capire quali sono.
Se non sbaglio, uno dei due del professor Montanari era acceso. Quindi se
Sì.
siete di fianco nella stessa aula, crea quell'effetto.
Adesso c'è un solo microfono acceso, come va?
Adesso va meglio.
Adesso sì.
Adesso guarda, tengo le chat qui.
Ok,
perché questo si vede solo questo.
Perfetto.
Quindi
direi che sia a posto.
Sì,
sì, se siete di fianco l'ideale è che parliate usando lo stesso computer.
No, ma adesso io mi assento e lascio solo il professor Navarra, quindi lui non...
Ok.
L'altro computer che vedete, io l'ho messo in registrazione, però ha l'audio spento, no, ha l'audio acceso ed è quello che funziona, quindi va bene. Perfetto. Ok, allora faccio solo un'introduzione rapida in inglese.
Ok, allora attivo
ok,
l'interpretazione.
allora solo un secondo che ci connettiamo.
Sì.
Quindi diciamo 4:30 devo finire.
Allora tu fai un break alle 4:30, poi riprendi alle 4:45 e in teoria fino alle 5:30, poi dopo vedi tu. Okay, so students, it took a long time to get prepared because, you know, with the new technologies and more sophisticated technologies, it takes some time. So just take our apologies. So I am pleased to introduce you Professor Antonio Navarra. He is professor at the University of Bologna, and is the director of the Euro-Mediterranean Center on Climate Change Research. I hope I used the correct definition in English. And he is a very famous international expert on climate change analysis and modeling and assessment of climate change impacts. You may know that the Euro-Mediterranean Center is producing several climatic scenarios up to the very far future for several emission scenarios, and therefore is carrying out a key activity in order to try to predict what the future climate will be. He will deliver today a presentation that last year was appreciated very much. I think it is very interesting. I would like to take this opportunity for thanking Professor Navarra for being here. And I hope you will enjoy this meeting, and please take the opportunity to ask questions in person if you are in the room, or with the micro of the chat if you are attending remotely. I will come back, Antonio, when you close, so to make sure that everything went fine. So see you later. Great. Thanks a lot.
Yeah.
And
a lot.
enjoy.
Thank you.
Bye-bye.
Thank you. Okay, thank you very much for this opportunity. I hope that the audio is working fine and everything is all right. And if there are problems, please let me know. Okay, so what's my task today? Well, my task today is, mission impossible. I have to tell you everything about climate change in these 6 hours that they've given me. And that's probably not possible. So what shall we do? I think that what I will try is that I will be happy if I will be able to put on your radar screen some ideas so that when you get out of this, we'll have some more food for thought, let's put it this way. And I also would like to try to sort of sketch the border of a problem that very often looks too big for us. It's one of the things that comes repeatedly in all the polls and the social investigation of how people relate with climate change. This idea that is something that is really big, really scary, but is sort of hanging out there and basically is incomprehensible. So the whole question is, how can we relate to the climate change problem? And the main point is how we can avoid to be ambushed by the future. So that is basically the whole, these are the terms of the problem. We would like to avoid surprises because we're a society in which we are, in a way, we don't deal well with surprises because everything is organized, everything is planned, everything must work with the clockwork. Surprises are not good. So the whole point is, and this is an ambition that is in a way very recent. You must have heard everything about the transition, the climate transition, the economic transition, and so on. Now, transitions like this are not new. We went through this kind of transition many times over. When we start using coal instead of wood, when we start using oil instead of coal. So transition had happened. But this time, we have the ambition to govern the transition. That is the main ambition. And maybe hubris, maybe we'll make it, but this is the difference. So we're trying to govern the transition in such a way that the costs and the damages and the opportunities will be much better distributed than in the previous transition. So the first thing that I need to do, I need to introduce what is climate. And climate is one of those things that everybody thinks that they know what it is. It's a word that is in a common vocabulary. And it's been known for a long time. This is a painting. This is a famous painting. There are lots of young people that apparently don't do anything. And there are these old guys that are actually trying to quarrel for whoever wants to get out first from the room. They're obviously professors. This is obviously university. This is the School of Athens by Raphael. It's a painting, it's in the Vatican. It is actually relevant to our story because one of those old guys is actually Aristotle. And Aristotle is the main character in this cast because he wrote the first book in meteorology ever written, the De Meteorologica. In this book, he's talking about climate change. And anybody from classic studies here? Can you help me translate? Strong disappointment. 5 years wasted. All right, so I will translate myself. So the De Meteorologica, Aristotle is talking about climate change. Now, in which way? His actually sort of argument, his argument is that climate change has changed because there was a difference between the climate of Greece at the time when he was writing and the climate as was described in Homer's books. So that's the heart of the argument. Now that's really strange, isn't it? That's not how we would go about to deal with the questions regarding the natural world. If you have a problem in the natural world, you don't go and look into some novel written 200 years ago, the answer, right? Probably you naturally think they should go out there and take a measurement or observe something, do something, not go to a library. So that's our attitude today. So that's the distance, the real distance between us and Aristotle. It's much bigger than the 2000 years that are in between us. At that distance is caused by the development that we have made in these 2000 years, because we have invented a protocol, a systematic way to deal with questions that regards the natural world. It's called the scientific method. So the heart of the scientific method is, if you have a question that regards the natural world, you have to make a measurement, you have to make an observation, you have to apply the science protocol to the problem. So our first question is how we do that with climate, how we apply, the science body of principles and methods and protocols and standards to this problem that is in a way so vague. And the climate, it is vague because it continues to be object of discussion by philosophers. And even Seneca was wondering about natural phenomena. It is very interesting. This is another interesting point, is marking the difference between the Romans and the Etruscans. And he says, well, they both think that there are messages from the gods in the lightning. But the Etruscans think that the clouds collide for the purpose of making a lightning and sending a message. The Romans thought that when the clouds collide, there is a message. Now, there is a very interesting difference. You see, it's a subtle difference. In the first case, there is a causality. There is a causality in the phenomenon. The phenomenon occurs because something wants them to happen. In the second one, they accept that there is a randomness to the events. They have meanings, but in some sense, they're random. So this creates an objectivity. This create the fact that the natural world is objective with respect to us. And that's part of the process in which we are building a relation with climate. And climate was changing, no question. In a period that was called the medieval optimum, the climate in the North Atlantic at least was particularly mild. And so the North Atlantic was almost open to navigation. The Vikings were able to settle in Greenland, maybe North America, and they built community. This is the photograph of Eric the Red, the guy that colonized Greenland. And this period, however, didn't last long, because something known as the Little Ice Age, around the 1300s, arrived, and in Europe, temperature became significantly colder. And for instance, the paintings of the period that depicts Europe in which freezing of rivers and lakes, including the Venice Lagoon, was common. And that's, of course, does not happen. This period sort of stopped around the 1800s. And this is known as the Little Ice Age, we call it today. But climate kept having very bad press, or at least everybody thought that they knew what it was. This is Leopardi. Every Italian students have sort of sweated on his poems. And it's interesting that in one of his Zibaldone is actually saying that the seasons are not what they used to be, that have changed. In particular, he says that there are no more half seasons or mid seasons, okay? Now, you must have an aunt or a grandmother that is telling you that there are no more mid-season anymore, in Italy at least. Well, if that's the case, she was absolutely right, because there are no mid-season in Italy. There have never been. The Mediterranean is not a place for mid-season, and we'll get to that. So At that time, people had an idea that climate was changing and there were these events. So you can see how the relation with climate was, what can I say, romantic, was certainly not scientific. Was something was part of your life, but in a way that was incomprehensible. And things get, from that moment on, the temperature has gone up. And you can see that this is the reconstruction of the last 1,000 years of temperature. And you see that the last 20 years or so, 30 years or so, have shown a drastic increase of temperature and basically a reversal of a cooling tendency that was more or less in place until maybe the 1900s. We'll get back to this. But again, climate kept receiving very bad press. This is Lorenzo Stacchetti. He was a famous librarian of Bologna Library and poet. And he was known as Olindo Guerrini. He was a pseudonym. He was also writing poems a little bit Osé with the name of Argias Bolenfi that I would encourage you to read. They're very, very nice. But he also is upset with spring. And so he makes this sonnet that is really upset with spring because it is making the leaves of the trees grow so he cannot see his girlfriend across the street. So everybody had a different view of what climate and weather was. In this case, was not particularly favorable. And then the most famous, how can I say, not enemy, but the worst invective against the weather, I think, is Eliot. The wasteland is one of the most famous lines in English literature. April is the cruelest month. Is that so? Is that really the cruelest month? Now, if I look at temperature in April in England, this is the daily change, daily variation of temperature over a year in 2002 in England. If I look at April, it's not particularly bad. So that's strange. Why April should have such a bad press? So again, you can see, if you look at weather, if you look at climate with anything that is the common language, or even artistic language, or you don't apply science, you can end up with very strange conclusions. I will skip that with making even more the case. So my problem is, how can I transform this relation and make it a relation in which I can apply science to climate? And if I have to do that, then the first thing I need to do is to present the system. So if this were a movie, this is the cast. So climate is made up of the atmosphere, the oceans, the land, the biosphere, the sea ice, the sun, and everything is more or less kept together by water. And water has these unnerving characteristics that you can find it liquid, solid, or as a gas, water vapor. Now, every time it changes form, every time it changes phase, exchange energy. Energy is needed or given out for any of these transformations. So when you evaporate water, so when water goes from liquid to gas, it needs energy. You must have cooked pasta once in your life, I guess. So you can see the process by which, if you don't turn on the stove, no water vapor, right? So every time that this happens, then of course you need the energy to make it gas. But then the problem is that the energy that we have needed to make water vapor is sort of trapped in the water vapor. And the water vapor travels. And when it goes back to liquid, when it condenses, it gives away the energy that was necessary to evaporate. So you see what's happening. What is happening is that it may happen that water evaporates here, then gets in the air, and gets transported somewhere else, where it condenses. We call it rain. And then heat released here, not there. So water vapor is a perfect energy vector. It moves energy around. The problem is that what is then climate in this context? Well, climate is not the instantaneous state of this system, but is the equilibrium state of the system with respect what? With respect the energy sources. But there is really only one energy source, right? That's the sun. So a better definition of climate is to say that is the state, the equilibrium state of the atmosphere, ocean, land system for a given solar input. So we give some solar input, the system will adjust to some equilibrium. That's climate. Now, how is that equilibrium? It's a complex equilibrium because it's not a static one. It's what we call a statistical equilibrium. So it varies all the time, but it varies within precise parameter envelope. Though that parameter envelope is the climate. So if you want to see a change in the climate, it's not enough that you see what the changes are. You have to look in the envelope and see if the envelope shifts. So that's a complexity. It's very complicated, and I could spend a couple of hours saying how complicated it is. It's very complex, and this depends on that. I can draw lines and so on. Look, it's very complicated. If you think of the most complex things you ever done, there must be something that you think that was the most complicated thing I've ever done. Okay, you multiply by 10 and you underestimating the complexity, okay? So how science would approach such a messy system? The basic idea of science is reduction. So you take a complicated thing and you start saying, well, this is not really needed, let's get it away. This one I can neglect it for the moment, and you take it away. This is not really essential, and you take it away. So that's how it works. So you reduce. I can reduce here. I spend that 10 minutes telling you water is a mess. Let's take away water. If I take away water, the problem is much simpler, much simpler. Actually, not that simple, but somewhat. But it's not our planet. So the problem I have is that I have an irreducible problem. That poses a question. How to go around if you cannot reduce, if you not apply the reductionist model of the scientific enterprise? So that's the first problem we have. But you might say another thing. You might say, well, do I really need to consider the entire planet? After all, I'm living here. So that's, of course, a legitimate concern. And of course, people for a long time thought that that was indeed the case, that local phenomena had the local origin. So if it's cold here, it's because something is happening here. Or if it's raining here. But it's an interesting story that at the end of the 19th century, this guy, Jevons, there is no pointer, okay. This guy, Jevons, he was not a climatologist, he was an economist. And if he was studying the problem of India and the economic sort of recurrent economic crisis that, the recurrent collapse of Indian agriculture. There were crises in 1861, 66, 76, 97. So periodically, there were problems with the monsoon. The agriculture would collapse, lots of problems. And so he was trying to understand why this was happening. Now, while he was analyzing those events, turned out that they were not limited to India. Almost at the same time, agriculture was failing also in China and Brazil. So he realized his argument, his idea was that these were not local phenomena, they were global phenomena. Something was creating abnormal conditions over the entire planet, so that agriculture would fail. Agriculture will fail as a sort of a leftover, because at that time, agriculture was strongly linked to a precise seasonal cycle. So people were expecting rain at a certain moment and so on. So any delay would collapse the agriculture. So, so he decided there must be something global. And he identified the origins of this in, guess what? In the only periodicity that he knew in the system. That's a sunspot cycles. You know that the sun has a 11-year cycle that is measured by the frequency of sunspots on its surface. So it goes up and down every 11 years, something like that. And there is variations in the intensity of the energy that the sun spits out. So he said that these crises were linked to the sunspot, to the sun 11-year cycle. On the basis of that, he tried to predict the next crisis. And it was a failure. That shows how much difficult are predictions. There is a varying, there is a quote that is varying attributed to a number of people, probably nobody knows exactly who said it. That basically says that predictions are very difficult, especially regarding the future. And this is indeed the case, but he didn't know that, but he actually had discovered something. The only weakness was the sunspot had nothing to do with it. What he discovered was that indeed those areas were connected. And it was due to another guy, Gilbert Walker. He was the director of the India Meteorological Service in the 30s. He had the same motivation. He wanted to find out if you could find a way to predict the monsoon so that agriculture could be organized. And he basically tried to connect statistically everything with everything else. In the process, he found out that there are long distance relationships on the Earth that connect variations in seasonal and interannual anomalies over a large part of the planet. These are these connections, in the modern term, we call them teleconnections. And now they've been investigated, they've identified extensively. And we now know that, for instance, when SST means sea surface temperature, when the temperature in the Pacific Ocean varies, say from one year to the next, or one season to the next, they cause variation in the temperature in the Indian Ocean. And when this temperature varies, then they affect the precipitation in Brazil, the monsoon in India, precipitation in Africa and the Sahel, and also the large-scale pattern of circulation in the mid-latitudes. So what this means, it means that the planet is covered with this web of interactions. So if you want, the climate was globalized much sooner than we tried. And the consequence is, and then if you try to a reduction, and you try to say, well, I'm not really interested in the climate of Australia. I'm in Emilia-Romagna. Therefore, I study Emilia-Romagna to death, put instruments all over the place, and we'll get the back, break the back of the climate problem in Emilia-Romagna. No, sorry, it doesn't work. Because what's happening here may actually be caused by some event that is happening on the other side of the planet. So if you want to consider climate, you cannot take even this route. You have to take the planet altogether. So we're stuck. What shall we do? We cannot reduce the problem in its complexity. We cannot reduce it geographically. What shall we do? how can we have a scientific consideration of climate? Because you see, if we cannot make reduction, this means we cannot apply the scientific protocol. Scientific protocol means that we have to formulate hypotheses. The hypothesis must be tested in an experiment so that we know which one is right, which one is wrong. I cannot simplify the problem, so it's difficult to formulate the experiment. And on top of that, I have a real problem making the experiments. Because you see, the culmination of the process of reduction of the science is a moment in which everything boils down to a single measurement, a crucial measurement. That is the crucial experiment, which result will basically deviate the world. And the photograph here is the photograph of such an experiment. This is the experiment of Michelson and Morley. If you know what it is, great. If you don't, it doesn't matter. What matters is that this experiment changed our vision of the world, changed our vision of reality. And what matters to me is that the entire experimental apparatus was on that table. So two guys working in a basement, I would say, on a table, have changed our vision of the universe. That's a crucial experiment. Now, I would like to make crucial experiments with the climate myself. I would like to close Gibraltar and see if the Mediterranean really dries up 2 meters per year, as my calculation says. Or I would like to remove the Alps and see if the climate of the Po Valley is really depending on the Alps. But they don't make me doing those experiments. They don't give me the money, and they don't give me the permissions to do this. So how can I make experiments with climate? So you can see this problem that I cannot make experiments is sort of crippled the development of climatology. If you take a climatology book of the 19th century, it looks like a travel log. I was in Bangkok, it was warm in the morning, then the fog arrived, something like that. So it was a descriptive science with some attempt of interpretation. But basically the idea was that there were, in a way, a static geographic view of climate. There were, people define climate zones so that, there are, if you go that way, you find that climate. If you go a little bit the other way, you find another climate. So it was an effort to classify almost a taxonomy of climates. But if you want to do a scientific consideration of climate, you have to make experiments. So how we sort of remove the impasse? Well, we were very lucky. We were very lucky because the basic physical and dynamical understanding of what are the forces that regulates the motion of an envelope of fluid over a rotating planet were known, were basically written down at the end of the 19th century. Unfortunately, those set of equations are a little complicated and they cannot really be solved with the tools of the analytical mathematics of the 19th century. So the only hope you can do to deal with such problems, that turns out to be, are the norm. Today we know that if you pick just a problem at random, the chances that you can actually solve it with analytical methods are 0. So we know that the norm is that most problems cannot be solved with analytical methods. So people develop one crucial observation. They sort of thought, okay, what is the real complexity of these equations? The complexity of this equation is in the complexity of the mathematical objects that are in their components. Mostly differential equations. But if you think very carefully, there are nothing more than arithmetic operations, repeated indefinitely. Everything that goes in those objects is basically a symbol for an infinite repetition of very simple operations. So if you truncate the process, if you say, I don't want to go to infinity, I want to stop first, then you don't have any more mathematical complexity. You have arithmetic. The only trade-off you have is that you have an enormous number of arithmetic operations. So either you do that very quickly or you're in trouble. But if you realize that, then we can take those sets of equations, transform them in this trade-off. And that's what today we call it numerical methods of discretization. And then boom, then you can actually get a solution. You get more than that, because what you get is a virtual representation of the system that they are representing. So they get a virtual representation of the Earth climate. Once you have a virtual representation of the Earth climate, if you've done your work well, then you can make experiments. Then you can take this virtual representation and close Gibraltar if you want. Or you can take away the Alps. Without being cheap, you can take away all the mountains of the Earth and see what the climate is. So this step, this capacity of creating this virtual representation was a decisive factor, because this allowed climatology to become a quantitative science. I would say allow it to become a science. Because now we can make experiments. Oh, by the way, these are the equations. I will always show them in case somebody finds a solution. Please contact me immediately. We can talk about that. And this is the guy that actually had the idea of discretization. His name is Lewis Richardson. He was a mathematician. He wrote a book about 100 years ago that's called Weather Forecast with the Numerical Methods. And you can see his basic idea. His basic idea was to perform the calculation at single points. So he chose this sort of grid of points, and he tried to make a calculation in which was able to push forward the state of the atmosphere in the future. Now, I think you've grown up enough. Why you can do that? Why you can use this equation to go into the future? That's not obvious. So we have to go back here one sec and simply look at the structure. On the left, time derivatives. Okay, what is a time derivative? It's basically a difference between two time points. So I can compute these later points from the previous points. So I can, step by step, I can go in the future. So the crucial point is that time derivative. I don't even need to know exactly the detail. The presence of that time derivative will give me an evolution. And because of that, I can actually make what people call now a time marching calculation. So step by step, you go into the future. Once you compute the next point, you use that as a starting point, and you compute another step. Well, you have to be a little careful. You cannot take a step of 1 year. There are tricks, but you can imagine. If it is too big, the approximation is bad, because that object over there is really valid for very, very small steps. So the steps must be small. And then there are people who devise rules to make sure that you get a step that can be stable, so that you can make this time marching calculation for a long time. Today, we're using routinely simulation that lasts thousands of years with time step of the order of 15 seconds. But at that time, he tried by hand. And so he tried by hand, and he tried to forecast pressure, actually 24 hours into the future. And it took him 24 hours to do the calculations, sort of useless, because, but that was not the worst part. The worst part was that it was a disaster. he was so discouraged that he basically abandoned the field. He never, wrote anything more about the weather forecast. He did numerical mathematics, and that's it. And the reason was the idea was good. It was actually incredibly smart, but unfortunately, he didn't know one or two things that were necessary in order to prevent the collapse of the time marching calculation. And these couple of things were, one was two things. One was some theoretical understanding of the property of those systems. The other one was that you cannot really do those calculations by hand. So you needed the capacity of making a lot of calculation fast. So in the late 40s, the first electronic calculators was available at the Institute for Advanced Studies in Princeton. And so this group of people made the first practical and successful simulation forecast of the atmosphere with the numerical method. So from that moment on, the models, this was a very primitive model. It was a model only one hemisphere, only one layer. So no three-dimensional structure in the atmosphere. By today's standards, I could run it on my laptop, not even on the laptop, into a Python notebook. At that time, they used a computer that took 3 rooms. Okay, but since then, things have grown quite a bit, and successive generation of models have appeared. That every time that there is a new model, it's like a new telescope for astronomers, or a new particle accelerator, is something that allows you to go deeper, to increase the resolution, to look farther into the working of the Earth climate. While all this was going on, there were a lot of discussion on the nature of the basic nature of the atmosphere variability, because it was clear that because of the continuous fluctuations in the system was fluctuating quite a bit. So the question was, how much can I follow those fluctuations? At that time, the problem was forecast, weather forecast. So I start today, how far in the future can I actually hope to predict? So it was a big discussion, and there was a fight between what we might call the deterministic group and the statistical group. The deterministic people thought that if you could get those equations, work very well on the numerics, work very well on the data, do a great job at doing things very accurately and precisely, understanding all the processes, then one could make the forecast. And the statistics were saying, no, you don't need that, because in the previous history of the atmosphere, there is all you need. And so by using statistical methods on the previous history, you can actually predict the future. Now, that's a very interesting point. It was not completely, baseless. But there are two catches. The first catch is, if the statistical model had to be successful, they were essentially linear. They were basically working on correlations. So in order for them to be successful, the atmosphere had to be essentially linear. So they set up an experiment in the 1960s at MIT to try to find out if the atmosphere was linear or nonlinear. Turns out that the atmosphere is nonlinear, as you might guess. So the deterministic people were very happy. So there was a tremendous effort to try to set up the system, the methods, how we work with that, and so on. So it looked like, road to success. Until Ed Lorenz discovered that if you take the deterministic approach and you make one single digit difference in the initial determination of the state. After 2 weeks, the forecast will have deviated as if you would have taken 2 random initial conditions. That was the start of the chaos theory that now morphed into complex system theory. And that's what the famous story about the butterfly that when the flap of a butterfly in Brazil can cause a hurricane somewhere else. No, it's true, but it takes a very large butterfly to do that. But, so basically, these deterministic ideas then were put in discussion. And there was a famous meeting in 1970 where these ideas were debated. So the question is, what is the right? That was the origin, let's put this way, of this extreme sensitivity to initial condition that really limits our capacity of doing weather forecast. We are actually capable of measuring what is the limit. We now know this between 2 and 3 weeks. So even if you had a perfect model, real predictability of the weather forecast is limited to 2-3 weeks. Now, why that's an issue? Because, everybody knows that, and then we start talking about climate scenarios. So the question is, but if you cannot predict the atmosphere 2 weeks from now, how can you talk about climate? That's a typical argument. And in the meantime, we're finding that the climate is even more complex than we thought. But let's go back. So why we can say anything intelligent about climate, even if we cannot predict the weather in 2 weeks' time? Well, because there are essentially 2 different problems. In a weather forecast, we are trying to make a very accurate, close statement about the evolution of the system, instant by instant. A forecast is something that I say, in 3 days, Bologna will rain at 4 in the afternoon. If it rains at 3 in the afternoon, forecast is wrong. But in climate, you remember, climate is the equilibrium state. So I'm not really interested in getting if it rains at 3 o'clock or 4 o'clock. What I'm interested is that in my climate model, we'll have to produce over a winter in Bologna the right amount of precipitation for that season. It's completely different. So I'm not making a forecast. What I'm aiming is the equilibrium state. If you want to be more precise, I'm aiming at the statistics of the atmosphere and the ocean. So what I want is the right number of days in which it's warm, or the right number of days that rains. That's what I want in a climate model. Now that's different. There is, it's a completely different problem. It's not affected by too much by the initial sensitivity to initial condition. And so that's why we can make intelligent statement about the climate. Then add another story. The climate is forces, I said, is the equilibrium state with respect to solar forcing. But the solar forcing is mediated. The energy that comes from the sun is always the same. But the way in which it is taken and transformed into environmental parameters like temperature, that's a property of our system. So if you change something in our system, then the same energy gets transformed differently. So what are we doing? We are doing an experiment like that, not in control conditions. We're changing the rules by which the solar energy is then transformed into temperature. One way of saying it is that we are increasing the greenhouse gases. That's correct. That's exactly how we're doing that. By increasing greenhouse gases, we're changing this rule. Now, from the point of view of the climate system, it's like an extra forcing. It's like you have added something that pushes the system systematically in one way. Now, those are things that model simulations can do very well. They can recognize the response to an external stimulus. So the other reason that we can say something intelligent about climate is that we are good at finding new equilibrium states. The models are very good at telling me what is the equilibrium state for a certain solar radiation at a certain set of rules by which the planet transforms the solar radiation into something else. That we do it very well. And we know that's mediated by the gases that interact with the radiation, both the solar radiation and the earth radiation, the thermal radiation. So the greenhouse gases, that's what they do. Now, this adding an extra complication, because until now I've spent some time telling you that nature is separate from us. It turns out it's not that separate, because our actions are actually changing the composition of the nature. Because we are changing the composition of the atmosphere, we are adding a loop in the system that was not there. So this picture is showing that basically the socio-economic development at the bottom, so the human system, is made up of many things: population, health, technology, trade, governance, policy. But this complex requires energy. Energy until now has been mainly obtained by fossil fuels. Fossil fuels will generate emissions of greenhouse gases. Greenhouse gases will concentrate in the atmosphere. They will change the rules. This will create climate change in the natural system. Climate change will present in several ways, mostly by changing the statistics of the atmosphere. And from there, you will get impacts. So it comes back to biting you. And then this will have impacts on the ecosystem, on water resources, so we'll see in details. And these impacts will affect the human system. And possibly they will feed back on the emissions. This is, in a way, the free loop. If you don't do anything, these things will go on. Most probably will amplify. So the two things you can do is to intervene in the loop are the two main policy options. That's mitigation and adaptation. We'll get back to that. But you see, mitigation and adaptation are the two attempts that we are making. We have, if you want, the two levers that we can move in order to act on this loop and try to stop the loop from amplifying without limit. Okay. And just to give you a feeling of what is happening, this is the increase of carbon dioxide. That's the major greenhouse gas from 1960 to last year. And it's pretty impressive, isn't it? You can actually see the economic crisis on this loop, on this plot, when the curve sort of slow down a bit. The interesting thing is that after every crisis, the slope is the same. So there is a crisis, the thing flattens a bit, and when the world starts over, it has the same slope. So even if you might think that it would be a good idea to be all poor so that we can drop the emission, it's not really a solution. Okay. You can also see in other interesting things, those fluctuations. Those are seasonal fluctuations due to trees. They're mostly dominated by the northern hemisphere seasons. When all the trees in the northern hemisphere put up leaves, they suck up carbon dioxide from the atmosphere, and you have a seasonal decrease in the carbon dioxide. When fall arrives and all the leaves fall down, then carbon dioxide go back into the atmosphere. And so you get this seesaw. To me, it's astonishing that you can actually see the seasonal cycle of leaves in the concentration of carbon dioxide. Now, let's look at the units. The units are ppm. Anybody knows what ppm is? Congratulations. Parts per million. Now, do we have an idea of how big is a part per million? Do you have a feeling what a part per million means? It's very, very small. Assume you want to buy a house. I'm sure that's on your thought last week. So you want to buy a house, and somebody said you see a house you like very, very much, it costs €1 million. You sort of check, you have 320 euros. So you're a little disappointed, but a friend comes and say, no, don't worry. I will give you 40% more of what you have. And so it gives you 80 euros. So now you have 400 euros. It's still very small. So if I look at this plot, I say, look, in 1960, concentration was 320 ppm. Wow, it's gone up a lot. Now it's 400, but still ppm. You know, it was a ridiculously small number before. It's a ridiculous small number now. So why should I worry? So the first thing that we have to, I'm not sure, let's see if I have the picture I want. No, I don't have the picture I want. Okay, let's go back here. So the first thing that I need to understand is how can I put this number in perspective? I have to give meaning to this number. It is difficult because it's very small. I cannot do it just by, hand waving. The one thing is for sure, I need to compute the detailed effect of this increase on the atmosphere. So I cannot do it, on a piece of paper with a pen. I need to compute all those factors, right? The water evaporating and then interacting and the clouds and this and that. So once I compute all this, basically I realize that the atmosphere has this tremendous capacity for amplification. There are processes there that will take small things and will amplify them. So it's only with the models that I'm actually capable of understanding what is the meaning of this. It turns out that this is a big deal. Actually, this increase, it's basically linked to the observed increase of 0.8 degrees that we have measured since the beginning of the 19th century, 20th century. And we have multiple, that's one, this is unfortunately. Okay, if you look on the left, that's in Celsius degrees. So that's that's what's happening to the planet. Things is warming up. We have an enormous amount of evidence that shows that this is linked to the greenhouse gases increasing. We know that the greenhouse gases are coming from the fossil fuels. The reason is that the fossil fuel have an isotopic signature. The carbon there is of a special kind, so we can find the same kind in the atmosphere. So it's coming from the fossils, it's not coming from somewhere else. So everything has been checked and rechecked, and that's what is happening. And in the meantime, if you look at why it's difficult, because the climate events are happening all over the place. So you have hurricanes, you have droughts. This is just 1 year, okay? This is just the major 1 year 2021 climate events. And they're basically extreme. The most interesting part of this picture, it showed that even if the Earth is warming, the way in which this warming may actually express itself, so the way climate change expresses itself, doesn't necessarily mean that it's always warming. So in some cases, it means more rain. So you have extreme events in which you have more rain. You have last year, the Arctic sea ice extent was at the minimum. Our climate simulations with increasing carbon dioxide shows that the Arctic sea ice is set to go probably by the mid-century. There will be no sea ice in the Arctic. So the most interesting part of this picture is the fact that shows that you have so many different things. And this, of course, will give you a complexity that is not enough. So when people say, oh, last week was really cold, what kind of climate change is that? That's irrelevant. The fact that is, the Earth is warming, it doesn't mean there will not be cold weeks. Just to give you a feeling, these are the anomalies for January 2021 with respect to 30-year period between 1980 and 2010. It was very warm in North America. So January 2021 was amazingly warm in North America over all the Mediterranean, but it was really cold in Siberia. So even if at the end, this will give you that a warming of the entire planet, you can see that the impact of different communities and locale is going to be different. In some cases, people may be happy. There was colder in rain this spring in Spain. In Spain, the rain falls mainly in the plain. No, so they probably get more rain. So this is a game in which somebody will lose, somebody will gain. And the Canadian probably were not too unhappy that January was a little warmer than usual. Of course, if that means that the permafrost melts and your infrastructure, including your pipelines, breaks because they're made on permafrost that's slowly sinking, you're not very happy. But you cannot have everything, right? The other interesting thing of this picture is Greenland. So January 21, Greenland was 5 degrees warmer than the long-term average. Now that's bad news, right? Because a warm winter means low accumulation of snow. This means that when the summer comes, there isn't a lot of accumulation from the previous winter. So the net loss of mass in the summer will not be compensated. So there will be a net loss. The other easy thing is that if I look at the Pacific, the East Pacific there is cold. And that's systematically low. It's like 3 degrees colder. That's because there are complex interactions in the Pacific that creates this really large anomaly. I want to point out the scale of these anomalies. It's enormous. It's the entire Pacific that's getting colder. And on the north, on the south, they're warmer. So the Pacific is so large that whatever is happening there will have global consequences. And then now we can look at climate from all sorts of different things. Surface temperature is the same that I showed this, unfortunately, for 2019. But the thing I want to show you two things. People now are monitoring lakes. So the one on the left over there are lake temperatures. And so people are measuring how much lakes were colder or warmer than anomalies. And you can see that there are a lot of warm anomalies. But the other thing that is interesting is that people have been monitoring the extremes. The extremes are the bottom picture. See, this is the number of warm days and cool nights. This means days that are above a certain threshold. Cool nights are nights that are below a certain threshold. And what you see is that the anomalies in 2019, the number of warm days were much larger than the history of warm nights all over Europe and China and Australia. The only place that were less than so was in North America. And the cool nights are moving in a consistent way. So cool nights were less in Europe, meaning there was an average warming. In Australia, it was more complicated. Some of them were less. In the Northern Australia were more. Now, Northern Australia is actually equatorial, okay? So That's more complicated than that. But this, I want to show you this because slowly the fixation of the climate problem discussion is often on temperature. But the multi-parametric nature of climate shows up. So you have many, many things to look at. And they're all behaving in a slightly different way. And you can have counterintuitive results by looking only at one piece. The other thing people are very much worried is precipitation. And let's see, let's just look at precipitation. It's the bottom right. These are anomalies from the long-term mean. So when it's green, it's extra rain. And where it's brown is less rain. Now that's very interesting. All our results indicate that the total amount of precipitation over the Earth does not change, but it shifts. In fact, if you look at this picture, you can see that there are negative and deficit and surplus are sort of coupled. That's because main precipitation area are moving. So they're leaving a deficit in the region where they usually are, and then they're creating a surplus where they move. This means that you get two kinds of issues. So you get the worst of both worlds, right? So you get a drought situation where the precipitation is not anymore. And then you get a flood risk where the precipitation moves. None of these two regions were adapted to it because they were adjusted to the traditional course of season. So if you expect, in some sense, it doesn't matter if it is an arid region or a wet region, as long as you know what's happening. But if a wet region suddenly becomes arid, you have a problem. If an arid region suddenly becomes wet, well, that's more difficult, but also you have a problem. So these shifts are how the climate change express in precipitation. So what about the future? Well, we don't know nothing about the future, right? Everything will depend on how much greenhouse gases will be in the atmosphere, and the amount of greenhouse gases will depend on what we do. So the only thing we can try to do is to set up stories, set up narratives, try to depict what kind of world will exist if you do certain choices, and what kind of world will be if you do some other choices. That's what these things are known as socio-economic scenarios. They're different from climate scenarios. They're all scenarios, but they're not climate scenarios. These are socio-economic scenarios, okay? So these are narratives about possible future society. For instance, if you think that nothing will happen and we will keep burning fossil fuels and actually energy demand will go up, the manufacturing will be highly distributed. So in order to make a car, you take the car, you send it to Argentina where they put the tires. Then everything is shipped over to South Africa when they put the mirrors. And then everything will go to UK where they put the steering wheel. So if production are going to be like this, then will be very energy intensive. And if it's not efficient, and if the energy is coming from fossil fuels, you will get a lot of emissions. And then you get the bottom, the top line, the gray line at the top. This is the, people can actually, once you make this story, you can compute the emissions that are implied by this kind of scenario, of narrative. And so once you get the emission, you can then get a profile. So the top scenario up there is, you know, the worst case, or at least the worst we can imagine in terms of fossil fuel consumption. And grossly speaking, that corresponds to a warming of the planet of the order of 6 degrees. Now, I say the order because at this point, you must come with me that there will be uncertainties. So we only say a range, okay? So it'll be of that order. But on the other hand, we can also make a narrative of the planet, where instead we will make every effort to reduce emissions and fossil fuel. We drop the fossil fuel. We make only renewables. Actually, we're so good that at some point we invent a method to take away carbon dioxide from the atmosphere. Those are known as negative emissions. Well, if you do that, then you get the blue line at the bottom. And you can see that the emissions start, these are emissions. The emissions start to decline. Then it becomes negative towards the end of the century, where these big plants to take away carbon dioxide from the atmosphere are in place. If you do that, we can keep the warming between 2 and 3 degrees. Now, these exercises have been going on for a long time. So the curve starts in 2000. The color curve starts in 2000. So those are stories. But the black line are observations. Those are the actual emissions. Now, if you look at the black lines, I would say 2 things. First thing was, wow, we were really good at making this scenario. The black line is within the range of our stories. So our stories are pretty good. The other thing that the observed emission is not clear, but I'm afraid are sort of aligned on the higher part of those scenarios. They don't seem to go like the lower ones. So that's not very satisfying. But the fact that in some sense we are centering the observed emission means the tools we are doing, the story we're creating, they're not bad. So which one of these paths we'll take will determine how much climate change we get. And in some sense, this is not a climate problem. This is a social problem, political problem. My duty as a scientist is finished. I'm simply saying, look, if the concentration is like this, then you get 5 degrees. If you do the other thing, you get 2 degrees. It's not my responsibility. You know, you are the policymakers, so you take a decision. Now, what about us? I told you that in the Mediterranean, there are no mid-seasons. Isn't it true? Why? Well, the Mediterranean is a special place. Huh? We know that. It's a border region. It's a border region historically, socially, demographically, economically. It's a border region also climatologically. It's basically at the border between the subtropical zone and the mid-latitude areas. Those are 2 different climatic areas in which different processes are important. Now, what does this mean? It means that basically in the Mediterranean, there are only 2 seasons. There is like a sort of an extended wet season from November to March, where the Mediterranean is basically in the mid-latitudes. The border shifts south during the winter. And then there is a dry season corresponding to a very relatively fast movement of the border north. So there are quick transition seasons, and then summer sets in, and you get a warm and dry summer. That's the Mediterranean climate. A little bit here, a little bit there. We like it very much. That's the national thing. And that's the Mediterranean climate. We like it very much. What is the catch? The catch is that the summers are dry and warm. In general, the weather is mild, but water resources are abundant because we get them in the winter. And why? Because there are a thing that are called storm tracks. These are the basically the path by which you must have seen on television, the perturbation coming from the Atlantic that sort of stroll towards Europe, carrying rain. There is a path to that. And in the winter, the Mediterranean is in that path. And so we get the rain. When the subtropical cell expands, then we push this path north. And so in the summer, we don't get that much rain and we get nice summers. That's the whole catch. Now, what happens with climate change? With climate change, the border moves north a little bit, maybe 400 kilometers, 500 kilometers, something like that. If you look at a global map, it's nothing. The planet is not going to be disturbed by it. For us, means that the dry season is longer. So everything is affected because now the dry season is longer, it comes early. So all the ecosystem, the plants are adjusted to a certain cold season that lasts so much and then suddenly starts over. So they have to adjust to this earlier start. It also means that there is less time for precipitation, right? So you can imagine, immediately guess there's going to be some problem with the amount of precipitation. In fact, the climate scenarios are indicating a loss of water resources or precipitation in the Mediterranean between 10 and 15%, depending on those curves. The bigger the emission, the lowest, the greatest the loss, okay? Now, 10, 15%, how much is that? Well, it's significant. You know, it's not a biblical catastrophe, but it's something that if you're a manager of water resources, you have to start worrying about. You have to start worrying about also if you're sort of planning infrastructure, and you have to make investments, and you have to decide, well, what shall I do? Shall I make that dam? And then if I don't get rain, why I made the dam? So it's something that has to be considered, and that is part of the issues. And these are the details. The details are that these are two scenarios. The one on the left is sort of the moderate scenario. The one on the left on the right is the most severe ones. These are loss of precipitation. And on top is the annual mean. In the middle, that's winter. And at the bottom, there's the summer. And so you can see the situation is complex because that loss of precipitation does not occur in a uniform way. So the south of Italy, generally speaking, as you move south in the Mediterranean, the loss becomes bigger. So for the islands and the south of Italy is more severe. Of course, is severe in the summer. But you can see that precipitation over the Alpine region increases. So this region will have another problem. They will have a flat problem. So at the same time, we'll have multi-risk issue, possibly with the multi-stressor thing. So the thing will couple. So we'll have drought and flood at the same time. That is very nice. And this is not just because the thing that increases our confidence, because how confident can be in that result? You know, there are many errors in those models. I know that. I write that, so I know. So instead of 50%, maybe 5% at the end. But it could be 40%, because the errors, uncertainties, have this habit of not going in the way you want, because they're uncertain. So the most significant fact is that the models indicate 15%, not 2%. So that's a very significant number that causes a very significant risk. And confidence in this result is increased by the fact that it's not something that's limited to Italy, it is part of a much larger pattern. This is the same picture, but now enlarged to the entire Mediterranean. And what you can see here is that there is a general shift of precipitation north. So the Earth is sort of shrinking towards the polar regions, carrying the area where it precipitates with it. So it's a very large pattern that shifts all this precipitation north in the southern hemisphere south. Models are very good at describing large-scale patterns. So confidence in these numbers is pretty high. Okay, so what are we doing about it? Well, you probably know at this point the IPCC. If you don't, I can tell you, IPCC is the Intergovernmental Panel on Climate Change, and it was created by WMO and UNEP. UNEP is the United Nations Environmental Program in 1988. It's an independent organization that is set up by government, and it has basically universal membership at this point. Even San Marino is part of it. So, 195 countries are part of IPCC. And what is the task of IPCC? Let's see if I have a slide. Do I have a slide? Yes, I have a slide. You see, the task of the IPCC is to assess on a comprehensive, objective, open, and transparent basis the scientific, technical, and socioeconomic information relevant to understanding the scientific basis of risk of human-induced climate change, its potential impacts and options for adaptation and mitigation. The other important thing is that, so basically they have to write a book. Okay, they have to write a book in which they're trying to make the state of the art. They try to say, okay, this is what we know. They should also try to explain how we know what we know. That is sort of an interesting thing. For a scientist, it's more interesting what we don't know and why we don't know what we don't know. But that's another story. But I understand for the policymakers, it's much more important to understand why we know, how we know what we know. So they basically have to write a book. These are called reports. And now we are at the 6th report. It's will be approved this week. But the other interesting thing, so they have to write this book in which they're basically making an assessment of what is the state of knowledge. And they have to try to more or less make also some sort of evaluation of the confidence that we can have in this knowledge. Basically, not only how we know what we know, but how well we know what we know. Now, the other interesting thing is that, of course, in order to get this, you can imagine this universal membership, there are countries and territories that have very different interests and problems. So IPCC reports should be neutral with respect to policy. Although they may need to deal objectively with scientific, technical, and socioeconomic factors relevant to the application of particular policies. So in some sense, you're asking me to do two really difficult things. Well, first, you ask me to establish what we know. Okay, that's fine. And then sort of you're asking me also to find some solutions and suggest some way of getting out of it, this relevant to application of particular policies. But then you're also asking me to be neutral, to be policy neutral. So the whole exercise then becomes something in which basically we try to put hypotheses on the table. And we try to say, okay, look, if you do this, this will happen. If you do this, that will happen. If you do that, that will happen. And we sort of retreat and then let policymakers to take a decision. But on the other hand, this is the only way in which you can have 195 countries to agree. Because the other thing people don't fully realize, these reports are approved word by word. It's a big room like this, bigger than this. And somebody is putting a text on the projector, and line by line, sentence by sentence, is asking for a consensus. So it's enough that somebody up there, raises his hand and say, no, I don't like that adjective, and then we'll start all over again, okay? So when people complain about slow progress in negotiations or, even in the process of producing these reports, I don't think they fully appreciate the process and the issues. Well, we'll probably get back to that. Anyway, so the IPCC is very important because at the end, you in some sense, you see at the end of this story, you come up with something that is our best effort. Sometimes it's not as good as we'd like, and we're humans. But basically, it has, I think, played a very nice role. One thing people don't fully understand or realize often is that it's not a scientific work. one of the rule of IPCC is that only things that are published can be quoted in the report. So sometimes you find that people reference reports. That's wrong. They should reference the original scientific work because there's nothing new in there. It's basically taken from somebody's work. So it's a very interesting concept. This started, this whole idea of making assessments. Now people are making assessments in various areas, but it is probably, and furthermore, was a very interesting exercise. Oh, that's a cycle. Okay, this is a 6th assessment cycle is underway. And IPCC is also making special reports. We made 3 special reports. One was what are the consequences of global warming of 1.5 degrees? Turns out there are impacts that you can measure. There is another special report on land, designed to make an assessment of climate change on land. Another one that was specific for ocean and cryosphere. And then the main report is almost finished. And there are 3 working groups, the working group 1, 2, and 3. The working group 1 is on the physical aspects of climate change. Working group 2 is on the impacts. Working group 3 is on the economic and social consequences. Roughly, working group 2 deals with adaptation, working group 3 deals with mitigation. The reports of working group 1 and 2 are already out, and the reports of working group 3 will be approved, as I said, this week. And then and this is all the timeline. In the fall, the synthesis report of the entire report will be discussed and approved. Now, these reports provide the scientific basis for the negotiation. The negotiation, the COPs, these are meetings that occur every year, or almost every year. And that's where countries are trying to get together to find a common policy to try to mitigate climate change. And let's see if I have, okay. Oops. Okay. Okay, I'll get back to the NFCC. So I'll skip this. Now, let's go back to the scenarios. This is what now people are developing models, not only of the climate models, that would be the natural system, but people are trying to model also the human system. So they started as economic model, and now they're including a lot of other effects like ecosystems and food security, population, infrastructure. These are known now as integrated assessment models. So they're trying to model the societal dynamics. They, as input, they get the environmental parameters from the natural climate models. So they get temperature, precipitation. Temperature, precipitation will impact agricultural production. Agricultural production will impact agricultural land values. Agricultural land values will have an economic effect, and so on. And then, now, from the integrated assessment model, they will produce emissions. So emissions will be produced by these models that in theory could be actually feedback into the natural climate models. So establishing for the first time the feedback. You know, the process I described before was sort of, in a way, separated, right? So somebody's making a story and then giving me the emissions, then I take this emission and I put them in a climate model. But by using integrated assessment model, I can actually close the loop, because now I can start from some temperature precipitation. I give it to an integrated assessment model. They calculate what would be the response to these changes because of land use change, agricultural practices, how often people use air conditioning, what's the energy demand. This will translate into emissions. And then emissions can go back into the climate model and feedback. In theory, you can do that. Not a lot of people have done that, but in theory, you can do that. And so we are going further. You know, we're trying to model not just the planet, but the entire human, if you want, human climate system. And this is now a more up-to-date tracking of the most recent emission scenarios versus observations. So these are now making until 2020. And what is happening is that once again, our scenarios are basically bracketing the observation of the emissions. So it's not too bad. Now, this is interesting because there was a change in this last version of the IPCC report. Rather than making, you know, these stories, people were making group of stories. They are called shared socioeconomic pathways. And they're sort of grouped in 5 groups. So SSP5 is the one where fossil fuel development is dominated by fossil fuel. So it's fueled by fossils. So this will give me the highest emissions. So the challenge in that context will be mitigation efforts. SSP3 takes into account the possibility of a fracturing of the world so that you have regional competition. Because this will affect the relations, this will affect the economic relation between regions, and therefore the different choices and the different will for collaboration. You see, mitigation requires collaboration. We have to mitigate all at the same time. If there is no collaboration, collaboration is low, then we have a challenge. Then there is SSP4, is where there are very, very large inequality in the world. So the countries, the region divides, and the inequality is such that there are a group of countries with very large income, a lot of resources, they can deal with climate change. And then there are a group of countries that have no resources. They are affected by climate change, but they cannot really adapt or do anything. And then, of course, there is SSP1, that's sustainability. That's the Goldilocks scenario, right? Everything nice. And guess what? There is an intermediate one in the middle. So that these are, to me, it's interesting that this is all we could imagine. There are no other possibilities of the future of the world. So I always wonder if that's the case, and you know, if there are some ambushes that are waiting for us. But what is happening? These are the global fossil emissions until last year. And this shows clearly 2 things. Well, first of all, that's the COVID drop at the end, when the world economy sort of stopped. And the 2008 drop, the economic crisis of 2008. And this shows very clearly what I was saying before, that after the crisis, the slope is the same. So there are some elements for optimism. Even if you forget COVID, the line seems to stabilize at a certain point. And it was the years where people were showing that there were positive signals on the side of what we call carbon intensity. That's how much emission per unit of GDP. So how much fossil it takes to produce a unit of wealth. That intensity was going down. So that means that overall, the world economy was getting more efficient. They were producing more wealth with less emissions. So it was good news.
Sorry, can you go back
to where?
The previous.
This one, yeah.
We have just mitigation without adaptation. So what I mean, is it possible to
Okay.
I think that we will have a lot of social problems.
Okay, no, the studies indicate that if you try to deal with climate change only with mitigation, you cannot make it. And the reason is some of climate change is already locked in the carbon dioxide is already in the atmosphere. At the present time, depending on the baseline, but basically another 0.8 degrees of warming are already in the carbon dioxide that is in the atmosphere. The reason is that there is a delay from the moment you put some carbon dioxide in the atmosphere to the moment in which it stabilizes, it gives you the maximum warming. It takes 20 years. So we are not really seeing all the potential warming of the carbon dioxide that is already there. So this means that we're going to get some climate change. So you cannot do only mitigation because some climate change will arrive. And so you have to do some adaptation. On the other hand, if you take the other view, when you say, I forget mitigation, we make adaptation. Then the cost will go up enormously. As a policy, mitigation in the long run is more efficient, cost efficient, they try to adapt to everything. So you have to do both. Okay, so what time is it? Okay, you want to stop for 10 minutes, maybe? It's 4:30. Let's stop. Okay. Oh, scusa. RCP. Radiation.
Anche avanti.
No, non sta. Radiation. No, qua non sta. Qua. Radiation pathways, radiation something. But more. Faccio prima qua. Representative concentration pathways. The point is that, scusami, il punto è che quei scenari lì erano quei numeri che vengono dopo. Sono il forcing di radiazione in watt. Quindi che succede? Succede che tu puoi avere lo stesso forcing di radiazione per combinazioni diverse dei gas. Quindi crea un po' di confusione, nel senso che è molto diverso. Cioè, dal punto di vista del clima non cambia niente. Se io ho 4 watt che vengono il carbonico oppure anche il metano, wow. Ma dal punto di vista delle politiche fa molto differenza. Allora quell'approccio lì è stato abbandonato, è stato usato invece quest'altro che è un po' diverso. E quindi
sarebbe la radiazione che arriva, cioè l'energia.
Sì, è il forcing radiativo corrispondente a quella concentrazione di emissioni. Alla fine, alla regina, che cosa cambia, quindi quando finisce quindi avere 4, a seconda dei numeri, 4, 5, 5.
Prima di arrivare oggi avevo un pensiero per il fatto quanto impatta la deforestazione sul problema della CO2. Però rispetto alla realtà che ha fatto vedere prima sembrava che appunto a livello di...
ma quella non è deforestazione.
No, esatto, però appunto sembrava che non impattasse.
No. L'impatto della deforestazione sta nella curva che cresce. Allora, le foglie non fanno altro che andare da un reservorio a un altro. Cioè, l'anidride carbonica che le foglie lasciano andare da punto, se la riprendono in primavera,
quindi non fanno niente.
Non fanno niente. Quello che succede è quando tu elimini dei pezzi di foresta secolare. Allora, quando tu togli la foresta, allora stai deforestando, perché intanto liberi tutto quel serbatoio di carbonio che sta negli alberi, che marciscono e quindi finiscono. E poi quello là non lo riprende più perché l'hai ammazzata la foresta, capito?
Però in sé per sé tiene soltanto lo status quo, quello non è che ne assorbe di nuovo, diciamo.
No, la deforestazione in realtà equivale a circa un terzo dell'aumento implicito. La deforestazione ti crea un aumento implicito dell'anidride carbonica, quasi un terzo dell'aumento è dovuto alla deforestazione.
Grazie. Perché dire una cosa?
Sì.
Sono uno studente di statistica,
Sì.
parto alla premessa. E per il percorso di studi che ho fatto, in realtà mi sto specializzando in ambito demografico e medico. E mi è capitato di fare un paio di corsi di demografia sociale e lì penso che tanto come qui, forse se voglio trovare più o meno un parallelo nelle due più grandi, diciamo, campi di interesse sociale e climatico poi sono collegati, mi perdevo in questa complessità, specialmente trovavo, diciamo, i modelli statistici che venivano in particolar modo nel campo demografico-sociale proposti per modellare migrazioni, fenomeni così complessi, come se lasciassero un po' l'amaro in bocca e soprattutto la sensazione che ho io, ma da giovane inesperto ancora, è che quando sei lì col computer a rannare questi enormi modelli, perdi, non solo mi sembra a volte di non riuscire a catturare la complessità, ma soprattutto perdi l'idea a volte di quello che stai facendo. E secondo lei volevo chiedere un suo parere su... Non lungi da me, diciamo, mettere in dubbio la scienza, insomma. Se di fronte a queste complessità così dei fenomeni, se la direzione che stiamo comunque al di là della politica, di tutte le proposizioni, se vede il futuro, se questa complessità secondo lei riusciremo un giorno, si riuscirà a maneggiarla sempre più?
Assolutamente. Cioè, in realtà quello che noi chiamiamo complessità è la nostra sorpresa rispetto a dei sistemi che non riusciamo a incasellare dentro quei 3 o 4 problemi che riusciamo a risolvere. Quindi il mondo è complesso. In realtà adesso c'è tutta una serie di sviluppi molto interessanti per affrontare questo tipo di problema, soprattutto per cercare di stimare le leggi dinamiche quando tu non hai a disposizione le equazioni, i principi fondamentali, ma dei dati stessi. Quindi tutto questo corpo che si è sviluppato adesso, quando la gente parla di artificial intelligence, c'è tutto un vocabolario romantico, ma se tu togli il vocabolario romantico, cosa sono? Sono tecniche non lineari, ricorsive, molto potenti di riconoscimento delle dinamiche interne di questi sistemi. Questo secondo me è il futuro, perché sai, in fisica tu hai l'equazione di Newton, quindi dove non hai dei principi fondamentali, non hai scelta, perché non puoi scrivere l'equazione della demografia, qual è? Boh. Però questo non vuol dire che non ci sia una dinamica, cioè non vuol dire che dentro non ci siano delle cose che funzionano. Allora questi metodi ti permettono di cominciare a ricostruire non con la differenza, mettila così, i metodi statistici regressivi si basano sul fatto che io sto cercando di modellare la dinamica del sistema usando semplicemente la relazione lineare che trovo lì dentro. Sì. Questi metodi allargano lo spettro, quindi guardano non solo relazioni lineari, ma anche relazioni non lineari. Okay. E quindi possono essere molto, molto efficaci.
Quindi diciamo questi metodi non lineari che ci sono possibili grazie all'avanzo tecnologico e alle simulazioni e a queste cose ci permettono di...
Non è solo quello, ci sono anche dei risultati teorici molto importanti. Per esempio, una delle cose, diciamo, sulle quali come dire, in genere ci si spacca la capoccia. I'm sorry, I speak in Italian, but you understand or I have to switch to English? Siete tutti italiani? Delusione.
Questa sono la...
No, vabbè, adesso... Ah, ma che ora è? Adesso, ok, faccio veloce, poi ti spiego. Okay. Allora, il problema fondamentale si chiama... ok, I'll switch to English. We're talking about the curse of dimensionality. Have you ever heard this?
Yes, because that's dimensionality, I don't know.
Yeah, the curse of dimensionality is when you consider the curse. So, okay, you're a statistician. Who else is no statistics here? One? You are? You're a statistician? No. What are you? You don't know. Agriculture. It's okay. I mean, you don't have to be ashamed. Okay, what are you? You're engineers. Okay, so you know math. Okay, you?
Engineering.
Oh, engineers. Okay, great. So when you do a regressive model, you try. Sorry. When you take. Okay, let's see. When you do a regressive model, you start with the time series. So basically, you have some sequence like this. Okay. And then you do lots of stuff on this. Now, if I want to do the same thing for climate, I have to do, say, on temperature over the Earth. Now, how many points I have for the temperature? When I started my career, the models were 5 by 5 degrees. So the entire temperature was divided in 5 by 5 blocks. So this means 360 times 180 divided 5 divided 5. So this is how much is that? Now I can very embarrassing. So well, okay, let's assume it is 10, 36 times 2. So this is 32 times 36. Okay. So this may be 70 by 30, 20,000 points. That was 50 years ago. The models we're using now easily have 500,000 points. Okay, so that's one temperature field. If I want to do the same thing, I'll have a time series like that. But each one of these will be a 500,000 vector. Now, if I want to apply all these relations, I will have a matrix that is 500,000 by 500,000. That is inconvenient even to bring in your back pocket. Okay. But recently, people have found ways of not considering the matrix this way, but this way. So now you don't do the matrix here. These are time levels. So you have 300 time levels. People have found that the same information that there is in this matrix is in a 300 by 300 matrix. So suddenly we can deal with these enormous problems. So we can apply these methods to fluid dynamics or complex things. So I think there is lots of potential. Okay, maybe I should go back after this digression. Okay, can I start? Well, I don't know if somebody's listening. I will start again. Okay, all right. So we were talking about emissions. Maybe I should start to wrap up. Okay, I think this is interesting. This is where the emissions are coming from. This is the energy used by source. Well, the energy, this is how energy is produced, okay? So oil is the main source. But you can see coal. And there has been a tremendous jump in usage of coal between after 2000, and natural gas has been continuously increasing. Coal are sort of flattened out at some point. Now, coal is the worst in terms of emission per unit of energy. So per unit of energy produced, it gives you most emissions. Gas is the best, natural gas. In the middle, there's oil. Now, renewables are below, and you can see that they've been also increased quite a bit in recent years, but there's still a portion of the total, in order to supply the energy demand, there's still a portion of the total. So this was basically showing what I was saying. This is now the emission by source. So by source, coal is by far the worst. So most of the emissions are coming from coal, and then there is oil, and then gas is not too bad, but it's because it's increasing, it's becoming a significant emitter. Now let's go one by one. Okay, these are emissions by China. And you can see that the blip in the increase of emission by coal are mostly due to China. setting up all these coal-fired plants after 2000. So China satisfied the energy demand of its growing, fast-growing economy, mostly by coal. Coal was abundant, cheap, so they make a... Then at a certain point, they decided there was a little bit of problem for air quality. And so they, officially, they, of course, they also contributed to the, it was good at that point to also contribute to the decrease of emission, but I think the real driver was the air quality in China, especially in Beijing area, that was becoming horrendous. So the curve flattened out and they started buying natural gas. This is US, and you can see the story of US here. Until 40 years ago, they were the largest consumer of oil, and they were also using coal. But since the year 2000, the coal has been dropping down as increases in gas is going up. So, and the reason is simple. That's the shale revolution. The availability of natural gas from shale made the oil gas much more convenient than coal. It was cheaper, it was cleaner, and was basically abundant. So the consumption of natural gas went up, and to the point that the fracking revolution is now US are the major producer of oil and gas. By the way, this has changed completely the geopolitical equations. I don't know if you realize that. So the bottom line is emissions in US are actually declining because of the declining usage of coal. And this is Europe. Europe is making a tremendous effort to improve efficiency because, of course, we have to import all energy. And so coal is also going down, but also oil. And the gas has been increasing and then stabilizing. So of the three major blocks, the European Union is the one that is actually decreasing emission most. And this is India. India is all coal. It uses very little natural gas. So it's all coal and oil. And this is the rest of the world. And basically the rest of the world is worth like one of these blocks. So you can see the problem. The problem is it's a little bit like a river. And everybody knows there is a fall, there is a cascade down river, but some people is in very large boats and some people is in canoes, and they're all going towards the fall, but the fall will not mean the same for all of them. That's what is happening. So we're getting towards this fall, but somebody's in a much more comfortable ship than others. They have more resources. Now, the other interesting thing, these are the emission per capita. Now, the emission per capita are interesting because they show you the evolution of the socio-economic system. For instance, the US has the highest emission per capita. The second one is Russia. And both have made efforts to become more efficient. In fact, the drop in the Russian emission is mostly due to the collapse of the economy in 1990. And they haven't really recovered. The thing that notice is China. Emission per capita in China are growing the fastest. In Europe are basically stable. Even India is not growing as fast as China. So these are, the ones that are basically, sometimes people is telling you about the carrying capacity of the planet. the planet has a capacity to digest some of the carbon dioxide that we put there. So not everything we put there remains in the atmosphere. Some of them get absorbed by the ocean, by the ecosystems, and so on. So you can make a calculation and see what would be the point where you are within the carrying capacity of the planet. And if you do it by capita, it's about 2 tons per person per year. So you see, for instance, US is overall of the order of 16 tons per year, but Europe is at 6 tons per year. But to let you know how difficult it is, if you take an intercontinental flight, so you go to US, that flight is 1 ton. So either you go there, you stay there, but if you go back, you have exhausted all your allocation for the year, okay? 2 tons. So it's difficult, very difficult. Well, okay, these are the total projections, so not very interesting. We've discussed this to death. So how we are reacting to this? Is the science system prepared for it? I would say no. And if you want a slogan, then I would say that universities have departments and society has problems, and they don't match. And one of the reasons is that we have shown that the traditional reductionist model is insufficient. There are problems that cannot be simplified. They're irreducible. Furthermore, the stresses, the problems that are coming from the world are pushing science to consider problems that are messy, multidimensional, ill-defined. It's those numbers that we don't have principle to understand them, to equation. And the emergence of new technologies have the potential to connect many different fields. The typical example is genetic and computer science. Genetic used to be a word of laboratories, now is a word of computers. Now you design proteins with computers. Of course, laboratory has not gone away, but it's something different. That means that the pressure against the traditional disciplinary barriers is increasing. But the research and academic system is not ready for it. We're still organized with disciplines invented in the 19th century, chemistry or physics. They didn't exist 300 years ago. We invented them. So the question is, are these adequate for the 21st century? Is there a way in which scientific disciplines should actually evolve like a Darwinian process, right? You create new species. So why do we should not have a speciation at creating new scientific disciplines? And we need to do that because of the challenge that is coming from the kind of problem we meet. And we have seen that. I mean, climate is going to be only the first, right? COVID, the pandemic, was another problem. Global problem, enormous socioeconomic implication, enormous science information value. Everybody wants to know what is the science, what do we know, when we know, how we know it. So the fact of the interconnection and the interconnectivity of our modern world will make these kind of problems more and more common. It will be very difficult over the next 40 years that one nation will have a problem only for them and not will be a global problem, because the connection will connect everything. So any problem will become everybody's problem. So there is a discussion, there is a conversation about this process. It's called convergence. And about 4 or 5 years ago, there was a very nice report by MIT, it's called Convergence, where the concept of convergence of disciplines was put together. So the merging of distinct technologies, processing disciplines or devices in a unified whole that creates a host of new pathways and opportunities. Means that different fields come together, there is collaboration among research groups, and the integration of the approaches that originally were distinct or were different, then become whole. So that principle, methodologies, values, and so on can be transferred and applied from one discipline to another. In so doing, you create a new world. So I think this is important. We have to rethink that in a world that maybe one lesson we can learn from climate where everything changed. It would be very weird that in a world where everything changed, we don't change. And this is part of the challenge we're having, because the adaptation is the other issue. The development of that convergence climate science is needed to develop the adaptation strategy and plan to deploy a successful adaptation plan. It means that I must have some information about what kind of climate changes impacts will arrive. Can I still grow corn in the Po Valley in 30 years? If I can, would it make sense economically? If I cannot, how can I keep the social texture together? How can I avoid that the social texture that has been built in many years will disappear? I can provide a future for the people when this thing will be changing. That's the issue that are into adaptation. And therefore, people are trying to develop a process by which one can address this issue one after the other. These people have invented, of course, that you have to have an engaging process in which stakeholders and decision makers and scientists, they all get together, and then you build adaptive capacity. Because adaptive capacity, the other part of the equation, we were talking about the ships before, but it's exactly the same thing here. If you have resource, let's put it this way, Las Vegas will never stay without water, because they have enough money that even in the middle of the desert, they will tank the water in if necessary. But if you don't have money, you don't have resources, then you're basically in the middle, or if you want, at the mercy of climate change. So how you deploy resources, how you do prioritize, how you distribute, how you get consensus from the community for the policy to be adopted, how you get social acceptability of the policies. So these are the question. And there are limits to adaptation. You cannot adapt to everything. So if Holland goes underwater because of sea level increase, we may probably convince the Dutch cows to do this, but I'm not sure what will happen to the cheese after all this. So there are ecological niches where adaptation cannot be done. The typical example are species that, in mountain ranges. So as the temperature increases, they try to go higher. That's true for, especially for plants, very colder. It seems at a certain point the mountain is over, so end of story. So there are niches where you cannot adapt. So what shall we do with these areas? What will be our priority in trying to preserve? We will have resources to preserve everything. These are the issues that you will have to face. So what are the consequences? So it's easy to paint terrible scenarios, right? So increased risks, migration, destroys of a community, destabilization, conflicts for scarce resources, especially water. Or we will have a path of increased solidarity and fair sharing of resources, and fueled and propelled by innovation and technology. So these are two distinct futures. And which one we will take, it's our choice. But one thing is sure, that it will be very difficult that policy decision will be taken just for climate change. But it will be impossible to consider any policy that does not take into account climate change. So it's already in the equation, and it will be there. And it will be there when people will have to design infrastructure, design investments. When people want to do risk analysis for investments, and so they want to know what is your asset value asset at risk. So all this now we'll have to take into account climate change, because the genie is out of the bottle and it will not go in. And the only guide we have is science in all this. Maybe I should not really need to tell you this, but you know, we have started the journey starting from Aristotle that didn't really have science. We have science. It gives us a guide to understand how the world works, but it's a very fragile conquest. It was not there all the time. If you think about it, basically we're talking about Aristotle 2,000 years ago. Modern science was about what, 300 years? So it's not given. We have to preserve the kind of attitude that gives us a fact-based attitude towards the world, so that we can be guided by rational thought rather than irrational thought or power wills. Thank you. I think I'll stop here. Yeah, that's it. I don't have anything else. Okay, thank you very much.
I have a question about the graphics. I didn't understand the graphics, maybe, but it seems that India is not a very polluted country on the graphics.
No.
Maybe I can understand.
No. India is emitting a lot. Let's see which one. This one, India.
But it's 1.6.
Yeah, but that is simply a measure of the dimension of the Indian economy. So you know the
India has a population of about
1.5, 1.2 billion.
Yeah.
Well, the economy is not as effective as the Chinese economy. So if you go and look at the Chinese, China is emitting 8 gigaton. Roughly, it's not totally fair, but roughly the consumption of the energy demand is proportional to the size of the economy. It's not totally fair because certain economies are more efficient than others. So, for instance, the European Union is emitting about 2 gigaton. Yeah. No, it's more because you have to add everything, of course. This is just by, it's not the total, sorry. No. If you want to have a size of the economy, you have to add all the lines, okay? Because these are total. So you have to add the emission from gas, the emission from, everything you have to add here. So you may get to 4 probably. But this is just the energy demand. What is showing you is that the energy demand in Europe is satisfied by a larger portion by the renewables, because they're not here. Okay? This is not the total energy demand, it's only the emissions. So, sure.
So India uses a major quantity of coal.
Yeah, the problem is that India does not have a lot of renewables. So this is almost entirely the energy demand. But the point is that if it goes through the same trajectory as China, because of that 1.5 billion people, then if you have to give the same amount of energy to all the Indians, then these curves will go even higher. So the question is that this country that are on a development path, they want to have the same development as we did. And the question is that they're trying to get there fast, in the fastest and cheapest way. We're trying to convince them that there is another way that does not really involve, harming the climate. But there is a discussion going on because they say that the problem was created by us because it was us who we put most of the carbon dioxide. So there is a discussion on basically what's the point.
We clearly know where it ends the responsibility of the sun activity and where it starts our responsibility in
No, I don't understand. Responsibility of what?
in climate change.
Yeah.
In increasing temperature.
No, I don't understand the first responsibility. Responsibility of whom?
Yeah, where it ends the responsibility of the sun.
The sun. Okay. The sun variability, you mean? Okay. Well, yeah, we know because we can make experiments just with. I can tell you one thing, that if we try to reproduce the climate of the 20th century, and we don't use the observed concentration of greenhouse gases, but we keep the concentration of greenhouse gases constant to say the level of 1900. We put every natural variability that we know of, like for instance, the solar variations and the volcanoes, everything we know. Then we are not capable to reproduce the evolution of the temperature in the 20th century. So the sun by itself is not, it cannot explain this increase in temperature, especially here.
Posso chiedere una parola? The coast of, riferito a, non ricordo la parola che mi ha detto, the coast of.
The curse of dimensionality. Curse. Okay.
Hai concluso?
Ho concluso.
Okay, thank you. Professor Navarra, thanks to you all for attending. And
Thank you. Bye bye. Oops, I don't know if you want to do something.
Chiudo la registrazione.